Hello, everyone. I hope you're all safe and sound. Welcome to the 17th lecture on analog and digital electronic circuits, which will be an introduction to high frequency analysis of amplifiers, in which we will study the high frequency models of transistors, their unity gain, bandwidth, and Miller's theorem, which is a useful method for analyzing amplifiers at high frequency. So far, we have analyzed amplifiers either in the mid-band frequency range, in which the gain is independent of the frequency because all the capacitive effects are ignored, or in the low frequency range, in which we consider only the effects of coupling capacitors. But at high frequencies, the internal or parasitic capacitive effects, which arise from the charge storage tendencies of the transistors, they become significant. So we know that the capacitive reactance is inversely proportional to frequency. So as the frequency increases, capacitive reactance decreases. So at large frequencies, when the frequency is large enough, the internal capacitive reactance becomes small enough that it cannot be ignored anymore. That is, it cannot be considered as open circuit anymore. So the pair of terminals of the device which are involved in the charge storage phenomena, they are inevitably coupled to the resulting capacitive effects. But in the analysis of the amplifier in the mid-band and low frequency ranges, these internal capacitive reactances are so large that we ignored them. But at high frequencies, these capacitive reactances, they become small enough that we cannot ignore them anymore. So the terminals which might have been considered as isolated while analyzing the amplifier in the mid-band or low frequency range can no longer be considered as isolated at high frequencies if they have an internal capacitance or internal or parasitic capacitor between them. Because at high frequencies, the capacitive reactance of such capacitors, it becomes very small that we cannot ignore it anymore. So this is called the shunting effect, which provides a rather low impedance capacitive path between the terminals, which wasn't there before when we analyzed the amplifiers in the mid-band or low frequency ranges. And this shunting effect tends to decrease the overall gain of the amplifier, as can be seen in this diagram. So this is the amplitude spectrum of the amplifier plotted against frequency. So in the mid-band, the gain is almost constant and independent of frequency. In the low band, the gain of the amplifier decreases because of the capacitive effects of the coupling capacitors. And in the high frequency band, the gain decreases again because of the internal capacitive effects. So this is the range of frequencies that we now want to analyze the amplifiers in. So the frequency on the higher side at which the mid-band, at which the gain drops below the mid-band value by 3 dBs is called the higher cutoff frequency. So this FH is now the higher cutoff or higher 3 dB frequency. So in order to analyze the amplifiers in this frequency, in this range of the frequency spectrum, we must augment the small signal models of the transistors by taking into account the charge storage phenomena that results in the associated internal capacitive effects. So I'll begin by augmenting the small signal model of a BJT with these internal capacitive effects. So in a BJT, there are two charge storage mechanisms. So when the BJT is operated in the forward active mode as an amplifier, then the emitter base junction is forward biased. This forward biased emitter base junction, for an NPN BJT, the forward bias across the emitter base junction injects electrons from the emitter side towards and into the base side. So electrons are injected from the emitter into the base, and within the base region, these electrons, they act as the minority charge carriers whose concentration decreases from the emitter-based junction towards the collector-based junction within the base region. And because of this concentration gradient, these injected electrons, they diffuse through the base from the emitter-based junction towards the collector-based junction, and then they are eventually collected by the collector. So for the time, the amount of time it takes for this injected electronic charge to diffuse through the base region, or in other words, the time it takes for this electronic charge to cross the base region. In that time, the base region is said to have this is said to store this electronic charge, which is injected from the emitter region into the base. And the amount of this charge which is stored during this time during this time in which they diffuse from the emitter-based junction towards the collector-based junction, during this time, the amount of charge stored in the base region is modulated by the forward bias voltage across the emitter-based junction. So greater the forward bias across the emitter-based junction, greater is the number of electrons injected by the emitter into the base region, and then greater is the electronic charge or minority carrier charge stored in the base region for the time that the electrons take to cross the base region. So this charge storage phenomena between base and emitter gives rise to what is called as the base charging or the diffusion capacitance between base and emitter. The other phenomena, charge storage phenomena, is associated with the stored charge in the depletion region. So there are two depletion regions in a BJT because there are two PN junctions. So depletion region is a carrier depleted region around a PN junction. So since there are two PN junctions in a BJT, there are two depletion regions, one around the emitter-based junction and the other around the collector-based junction. So this is formed as a result of diffusion of holes from the P side towards the N side, and by the diffusion of electrons from the N side towards the P side of the PN junction. So as the diffusing electrons they move from the N side towards the P side, they recombine with some of the holes at the boundary of the junction on the P side. And similarly, the holes diffusing from the P side towards the N side, they recombine with some of the electrons available at the boundary of the junction on the N side. So this recombination creates a net positive charge on the N side because of the loss of electrons due to recombination, and a net negative charge on the P side because of the loss of holes due to recombination with the diffusing electrons from the N side. So this bound positive charge on the N side and bound negative charge on the P side makes up what is called as the depletion region. It is a carrier depleted region because all the electrons diffusing towards the P side, they will recombine with the free holes available at the boundary, and all the holes diffusing from the P side, they will recombine with the electrons available at the free electrons available at the boundary. So this depletion region is a carrier depleted region, which is also called the space charge region. So this space charge region stores bound positive charge on the N side and bound negative charge on the P side. The amount of charge as well as the width of the depletion region is a function of the voltage across the PN junction. So the amount of charge modulates with the change in voltage. So changing the voltage will change the charge stored in the depletion region. So this gives rise to what is called as the junction capacitor. So there will be two junction capacitive effects in BJT. One due to the charge stored in the depletion region around the emitter-based junction, and the other one due to the charge stored in the depletion region around the collector-based junction. So the diffusion capacitance is quantified by the electronic charge which is injected by the emitter into the base region. So as the electrons injected from the emitter side into the base region, as they diffuse through the base region, they constitute, like I said, they constitute minority carrier charge stored within the base region. And this charge, which is denoted here by Qn, it can be quantified like this in terms of the collector current, IC, and tau f, which is called the forward base transit time. And it represents the average time which is required by the electrons to cross the base region or to diffuse through the base region. So during this time, the base is said to hold this electronic charge Qn, which is given by this relation. So, and it makes sense as well, because current is defined as charge per unit time. So Qn charge takes tau f amount of time on average to get through the base region. So this flow of electrons to the base region eventually constitutes what is called as the collector current. So IC is Qn over tau f, which gives Qn as tau f times IC. So we know that IC has an exponential dependence on the base emitter voltage, which means that Qn will have, because Qn is proportional to IC, so Qn will have an exponential dependence on base to emitter voltage, which means that small change in base emitter voltage will induce large change in Q1, large nonlinear change in Q1. This is a nonlinear dependence. So the resulting capacitive effect is highly nonlinear, it's exponential. Capacitance is defined as the change in charge. For a linear capacitor, we define the capacitance as charge per unit voltage. That is the change in charge per unit change in voltage. So in this case, a small change in voltage induces a large change in charge because of the exponential dependence. So the capacitance is not linear anymore. It is highly nonlinear. The associated capacitive effect is highly nonlinear. So we cannot define the capacitance simply by the ratio of charge and voltage. So what we do is we define the capacitance, the base charging or the diffusion capacitance for small signals. That is for signals which satisfy small signal approximation. So for such signals, we define the small signal base charging or diffusion capacitance by the rate of change of the stored charge within the base region with respect to the base emitter voltage, and we denote it by C subscript DE. So the diffusion capacitance is defined as the rate of change of charge with respect to the base emitter voltage. So putting the value of charge from 1 in here, we see that CDE is given by the rate of change of collector current with respect to the base to emitter voltage. So for small signals, we know that this represents the slope of ICVBE curve. And for small signals, we know that the slope of ICVBE curve at a fixed point on the curve, which is the bias point. The slope at the bias point on the curve is very well approximated by the slope of the tangent, slope of the straight line, which is tangent to the curve at the bias point. So from our small signal analysis, we know that this slope of the ICVBE characteristic at a given bias point is called the transconductance, is given by the transconductance of the device. And since for small signals, for small change in VBE, the corresponding change in IC is linear. So we can replace this derivative by the change in IC by the ratio of change in IC to change in VBE, because the change in IC for a small change in VBE is linear. So we can represent this derivative like this in terms of the small signal quantity, which is equal to GM, of course. So given a bias point on the ICVBE characteristic, for small signals, we can very well approximate the change in collector current. For small change in VBE, we can very well approximate the change in collector current through the linear slope of the characteristics at that point, which is called the transconductance of the device, which in turn is given by the bias point. So it is given by the DC component of the collector current and the thermal voltage VP. So from this relation, we conclude that for a small change in VBE, which is equal to small VBE, the change in charge dQn, which is equal to tau f times DIC, which is equal to tau f times small ic, is given by CDE times VBE. So CDE times VBE quantifies the small change in the electronic charge Q1, which in turn is given by tau f times small ic, and tau f times small ic in turn is given by tau f times small VBE times GM. So for a small change in VBE, the corresponding small change in Qn is given by CDE times VBE or tau f GM times VBE. The junction capacitance associated with the reverse bias collector based junction is given by this expression, in which C mu naught. So C mu is the reverse bias junction capacitance of the collector based junction, and C mu naught is its value at zero bias, and VCB is the reverse bias voltage across the junction, the collector based junction. V naught is the built-in junction voltage, which has values typically in this range, and M is called the grading coefficient, which defines the doping profile across the PN junction, and is typically found to have values in this range. So for abrupt junctions, that is the junctions for which the doping concentration abruptly changes from holes to electrons as we move across the junction from P to N side. Such junctions are called abrupt junctions, and for abrupt junctions, the value of grading coefficient is 0.5. So typically for abrupt junctions, you will see that you will see in this expression a square root in the denominator because M is 0.5. For other types of junctions, which are called graded junctions, in which doping concentration changes gradually from one side of the junction to the other, M takes on values which are less than 0.5 and in this range. The junction capacitance associated with the forward biased emitter based junction is denoted by C subscript JE and is approximated under the assumption of an abrupt emitter based junction by this value twice CJE naught, where CJE naught is the zero bias emitter based junction capacitance. So basically you can use this expression in 3 to derive an approximate relation, the approximate relation given here in 4. So instead of minus VCB for the forward bias emitter based junction, we'll have plus VBE here, and M under the assumption of abrupt junction will be 0.5. So we'll have a square root of 1 plus VBE over V naught. So if we assume, because in the forward bias, the emitter based junction voltage is roughly about the order of V naught. So if we assume that VBE is about 0.75 times V naught, then under this approximation, you can get this result given in 4. So take into account these 3 capacitive effects, that is the diffusion capacitive effect, the forward biased emitter based junction capacitance, and the reverse biased collector based junction capacitance. We can augment the small signal hybrid pi model of a BJT like this shown in this circuit. So C mu is the reverse bias junction capacitance between collector and emitter. So at low frequencies, at frequencies in the mid-band range or in the low frequency range, the base and collector terminals, they were isolated. But at high frequencies, because of the capacitive, because of small capacitive reactance associated with this C mu, we cannot assume them to be isolated anymore. And hence they get coupled through this capacitance C mu. And C pi here is the total capacitance between base and emitter. That is, there are two capacitive effects between base and emitter. There is the diffusion capacitance, and then there is the junction capacitance. So since capacitors in parallel add, so we add the two, and we call the result as C pi. So C pi is the total capacitance between base and emitter, taking into account the junction capacitance and the diffusion capacitance. For the MOSFETs, we have already seen the charge storage phenomena in the induced channel in the form of the oxide capacitance per unit area, or which is also called the gate capacitance per unit area. And we denoted it by Cox, which was equal to epsilon ox over Tox, where epsilon ox is 3.9 times the dielectric constant of vacuum, and Tox is the thickness of the silicon dioxide insulator between gate and channel. But there is no, so this capacitive effect, this capacitance exists between the gate, the polysilicon gate electrode, and the channel, but there is no channel terminal. So this capacitive effect cannot be modeled as it is in the circuit because there is no channel terminal. So this capacitive effect between gate and channel is then modeled between gate and drain and gate and source terminals. Furthermore, we have depletion region between a reverse bias junction and a depletion region between the source and body regions and the drain and body regions, which will result in the source body and drain body junction capacitances. So both of these capacitive effects, that is the gate capacitive effect and the junction capacitive effect, must be taken into account for the analysis of MOSFET circuits at high frequencies. The gate capacitance between polysilicon gate electrode and the induced channel, it depends on the mode of operation of the device, because the profile and the depth of the channel, it depends on the mode of operation of MOSFET. So when the MOSFET is operating in triode mode, the induced channel has uniform thickness all the way from the source end towards the drain end, and the gate to channel capacitance, which is given in this case by Cox times W times L, is approximately modeled by dividing it equally between gate source terminals and gate drain terminals. So we denote the capacitance between gate source due to channel by C subscript G CS. Similarly, C subscript G CD denotes the capacitance between gate and drain due to channel. And both of these capacitances, they are equal to 1/2 times Cox times W times L. On the other hand, if the MOSFET is operating in the saturation mode, then the depth of the channel, it reduces from the source end towards the drain end. Furthermore, there is no channel at the drain side. The channel is pinched off at the drain, which means that the capacitance between gate and channel, the capacitance between gate and drain due to channel will be 0 because there is no channel on the drain side. So all of the capacitance between gate and channel is modeled as C subscript GCS. That is, it is modeled as the capacitance between gate and source due to channel. And in this case, it is given by 2/3 times Cox times W times L. And like I said, the other component between gate and drain is 0 in this case. In the cutoff mode of operation, that is when the gate to source voltage, or the case of an NMOS, is less than the threshold voltage, there is no induction of the channel. There is no channel. There is no channel induced in the body of the device. And then since there is no channel, there is no capacitance between gate and source due to channel and gate and drain due to channel. However, the silicon dioxide layer of the insulator now exists between the polysilicon gate electrode and the body of the device. So the capacitance Cox times W times L, which was the capacitance between gate and channel in the triode mode, now is modeled as the capacitance between gate and body. So in the cutoff mode, capacitance between gate and body is given by Cox times W times L. So the total gate to channel capacitance is then, which is denoted by C subscript GC, is then given by the sum of these three components. That is, it is given by the sum of CGB, gate to body capacitance, CGCS, gate to source capacitance due to channel, and CGCD, which is the gate to drain capacitance due to channel. There is another component of the gate capacitance, and this component is associated with the lateral diffusion in the device. So lateral diffusion refers to the diffusion of the source and drain regions under the silicon dioxide layer. So this small protrusion of the source and the drain regions under the silicon dioxide is referred to under the layer of the silicon dioxide dielectric insulator is referred to as lateral diffusion. So now that we have an overlap between the polysilicon gate electrode and the electron-rich source region, as well as the polysilicon gate electrode and the electron-rich drain region, which are separated by this silicon dioxide dielectric. So you can think of this overlap as forming another parallel plate capacitor, whose capacitance, which is called for the source side, the gate to source overlap capacitance, and for the drain side, the gate to drain overlap capacitance, denoted by CGSO and CGDO respectively, is now given by the capacitance per unit area times the area of the overlap. So denoting by L subscript OV the amount of protrusion of the source and drain regions under the silicon dioxide layer, we see that the length of the overlap is L subscript OV, and the other dimension of this overlap is the width dimension, which is perpendicular to the plane of this slide. So the area of the overlap is then given by width of the channel times LOV. So the overlap capacitance for the overlap between gate and source and gate and drain, these capacitance values, they are given by Cox times the area. So because Cox is the capacitance per unit area, so it is given by Cox times the area of the overlap, which is W times LOV. And it is also commonly expressed as COV times W, where C subscript OV is the overlap capacitance per unit width of the device. So these two components, that is the component of the gate capacitance due to channel and the component of the gate capacitance due to overlap with the source and drain regions, they define the total gate capacitive effect in the MOSFET devices. So here in this table, I summarize the values of all the components of the gate capacitance and for different modes of operation of the device. And I also list the overall gate capacitance, which is denoted by CG. So in the cutoff mode of operation, there is no channel. So CGCS and CGCD, they are 0, but there is capacitance between gate and body. So the gate and channel capacitance, which is given by the sum of these three components, is equal to Cox WL. And the total gate capacitance which is given by the sum of the gate to channel capacitance and the overlap capacitance between gate source and gate drain, is given by this expression. So this is the component due to channel, and this is the component due to the overlap between gate and source and gate and drain. In the triode mode, we have a uniform depth channel. So there is no capacitance between gate and body because body is isolated from the gate terminal through the channel. So that uniform depth gives rise to capacitance between gate and channel, which is equally divided between gate and source and gate and drain. And the sum of these three, which is again equal to Cox times W times L, gives us the total capacitance between gate and channel. And adding to this, 2 COVW gives us the total gate capacitance in the triode mode, which is again equal to the gate capacitance in the cutoff mode of the device. In the saturation mode of operation, there is no gate to body capacitance, and there is no channel at the drain side, so EGCD is 0. So the gate to channel capacitance is given by 2/3 times Cox times W times L, which is the value of the gate to source capacitance due to channel. And then adding again 2 times COV times W to this value gives us the total gate capacitance in the saturation mode of operation. Junction capacitance associated with the reverse bias source body and drain body junctions. They are given by expressions which are similar to the junction capacitance for a reverse bias collector-based junction. So denoted by CSB and CDB, these represent the reverse bias junction capacitance between source body and drain body. Whereas before, CSB0 and CDB0, the values of the respective junction capacitances at zero bias. VSB and VDB are the reverse bias voltages between source to body and drain to body junction, and between source to body and drain to body region. And V0 is the built-in junction potential or built-in junction voltage, and M is the grading coefficient, which defines the doping concentration or the doping profile across the junction. So there are actually 4 components contributing to the junction capacitance, both at the source to body junction and at the drain to body junction. So if we look at this cross-sectional diagram, then if you can visualize the 3-dimensional view of this source region. So this source region is immersed in the substrate, in the P-type substrate. So there is a junction at the bottom side of the source region between source and body. There is a junction at the front face between source and body. There is a junction at the back face between source and body, and there is a junction at this side wall, at this side face between source and body. There is no junction on this side because this side of the source region faces the channel. So there are 4 components. There are 4 PN junctions. One at the front face, one at the back face, one at this side face. So these are called the junction capacitances due to side walls. And then there is a PN junction at the bottom side of the source, which is called as which gives rise to junction capacitance at the bottom of the source region. The grading coefficient for the PN junction at the bottom of the region can have different values compared to the grading coefficient for the PN junction at the side walls of the region. So if the capacitance is at the zero bias, they are specified as capacitances per unit area. Then one must compute the total junction capacitance, which is denoted by C subscript JS, which is the junction capacitance between the reverse bias, the total junction capacitance between the reverse bias source and body regions. It must be computed for the bottom PN junction and the side walls and the PN junction at the side wall separately. So the capacitance, the junction capacitance associated with the PN junction at the bottom of the source region is given by CSB, which is the value obtained from this expression at a particular reverse bias. Because CSB naught is given per unit area, CSB will be a capacitance at the reverse bias voltage VSB per unit area. So this must be multiplied by the area of the bottom plate of the or the bottom side of the source region. So if we denote the length and width of the source region by LS and WS respectively, then the area of the bottom region of the bottom side of the source region is given by WS times LS. So CSP times WS, the CSP times WS times LS gives us the junction capacitance for the PN junction between the source and body at the bottom side of the source region. On the other hand, due to the side walls, so again we compute the source to body capacitance CSP from this expression at a particular reverse bias value, and since it is given, it is specified as per unit area. So for the side walls, since there are 3 side walls, the front, one at the front, one at the back, and one on the left side of the source region. So we must multiply this capacitance per unit area by the area of these 3 side walls. So if we denote the depth of the source region within the substrate, so if this dimension, this vertical dimension, which is the depth of the source region within the substrate, if this dimension is denoted by xj, then xj times ls will be the area of the front side and the back side. So ls denotes this dimension of the source region. So xj times ls is the area of the front face, and it is also the area of the back face. Similarly, xj times ws, which is the width of the source region, which is the dimension, which is along the dimension perpendicular to the plane of this slide. So xj times ws will give us the area of this side plate, of this side of the source region. So xj times ls times CSB is the junction capacitance due to the reverse bias junction between source and body at the front and at the back side of the source region. So we multiply it with 2 because we add them. So CSP times xj times ls plus CSP times xj times ls will give us 2 times ls xj CSP. So this accounts for the junction capacitance at the front and back face of the source region, plus CSP times xj times ws gives us the junction capacitance associated with the PN junction at the left side wall of the source region. So when we add the 3 components, we can take CSP xj out common, and what we are left with, this here 2ls plus ws is called the perimeter of the source region. So oftentimes we express this quantity CSP times xj as CSB subscript side wall SW, CSP subscript SW, which is called the source to body junction capacitance per unit perimeter of the source to body junction. So the total junction capacitance between source and body due to the reverse bias PN junction between source and body is then given by the sum of these 2 terms. So we can carry out a similar analysis for the drain side as well, in which if we denote the length, width, and depth of the drain region by LD, WD, and XJ respectively, then we obtain analogous expressions. We can obtain similar expressions for the total junction capacitance between brain and body like this. So taking into account all of these capacitive effects, we can augment the small signal hybrid pi model of the MOSFET like this, as is shown in the diagram here. So we can have capacitance between gate and drain, between gate and source, between gate and body, and between drain and body. So the capacitance between gate and source, there are different components to this capacitance between gate and source. So there is the capacitance between gate and source due to the channel, and then the other component is the capacitance between gate and source due to the lateral diffusion, which is the overlap capacitance. So since both of these capacitive effects, they exist between gate and source, and capacitors connected in parallel, for the capacitors connected in parallel, the equivalent capacitance is given by the sum of the capacitances. This capacitance CGS is the total capacitance, which is the sum of the gate to source capacitance due to channel and gate to source overlap capacitance. Similarly, there are two components of the capacitance between gate and drain. Both of them are added. So the first component is the gate to drain capacitance due to channel, and then the other component is the gate to drain overlap capacitance. So the two components are added, and the net capacitance between gate and drain is denoted by CGD. CDB is the total junction capacitance between the reverse biased associated with the reverse biased drain to body junction, and because oftentimes the source terminal is directly connected to the body terminal. So in this model, I've assumed that the source and body terminals, they're connected to each other, which eliminates the source to body reverse bias junction capacitance. So this is the high frequency small signal hybrid pi model for the MOSFET, which can be used to analyze MOSFET circuits at high frequency. So because of these capacitive effects, the intrinsic gain of the devices, it reduces and drops at high frequencies. By intrinsic gain, I mean the beta of a BJT, because BJT has an intrinsic current gain. It is a current amplifier. And for the MOSFET, the intrinsic gain is the GM, which is the transconductance. So these intrinsic gains associated with the transistors, because of these capacitive effects, they drop at high frequencies. So ideally, we would want these intrinsic gains to have a flat spectrum against frequency. That is, we want the intrinsic gain to be independent of the frequency and not drop at high frequencies, but that is not possible because of these capacitive effects. So it is desirable to have these gains drop at as large a frequency as possible, because then the intrinsic gain would be independent of the frequency for a larger portion of the frequency spectrum. So a figure of merit for the high frequency operation of the transistors, which can be used to rate the device and in fact rate the use of the device as an amplifier. It's called the unity gain or transition or transit frequency, and it is denoted by F subscript T. So this frequency, which is a measure of the intrinsic speed of the transistor, is defined as the frequency at which the short circuit current gain of a MOSFET in common source configuration, or the short circuit current gain of a BJT in common emitter configuration, it drops down to 1. So it becomes, so the frequency at which the corresponding short circuit current gain, they become unity, defines the unity gain or transition or transit frequency for the respective device. So like I said, we would want the short circuit current gain to be independent of frequency ideally, but since that is not possible, so we would want the short circuit current gain to be independent of the frequency for as large a portion of the spectrum as possible. In other words, we would want a higher value for the unity gain frequency, and higher the value of the unity gain frequency for a device, better is the device as an amplifier. The unity gain frequency for a bipolar junction transistor can be found by solving this circuit. So this is actually the small signal model of BJT. And since we are working only on the device, there is nothing else. There is no other component. So we excite this BJT at high frequency with this current IB, and we short circuit the output. So the current going through this short circuit into the collector is denoted by I subscript O comma S. So this current, because of the short circuit, we can realize that this end of C mu is directly grounded. So C mu is actually in parallel with C pi and R pi. So the voltage across C mu is then given by V pi. The voltage at this node with respect to this node is actually the voltage at this node with respect to this node. So the voltage of this node with respect to this node is V pi. So V pi over the capacitive reactance of C mu, that is V pi over X C mu, gives us current flowing in this direction. So V pi over X C mu is S C mu V pi. So S C mu V pi gives us current flowing in this direction from left to right. So this current and this current, because R naught is shorted out, so R naught won't contain any current. So IOS plus this current gives us GM V pi. So IOS can be written as GM V pi minus the current flowing through C mu, which is S C mu V pi. On the other hand, we can write V pi as the current flowing into the base times the impedance at the base. Impedance at the base is given by the parallel combination of C pi, R pi, and C mu. So R pi in parallel with XC pi in parallel with XC mu is the impedance between base and emitter, or base and ground, because emitter is grounded. So this is common emitter configuration for the BJT. So V pi is given by IB times this equivalent impedance, which can be written like this. So the parallel combination can be written as the inverse of the sum of the inverse of the individual elements. So I can write V pi S like this. So I can put V pi in here and take IB onto the other side to find the ratio IOS over IB, which is the short circuit current gain, which is denoted by H subscript FE, and it is obviously a function of the frequency. It is also denoted by beta, because remember we call beta as the current gain of the BJT in common emitter configuration. So we refer to this short circuit current gain as beta as well. We denote it by beta as well. So this ratio, which is obtained by substituting V pi in this expression, is given by GM minus SC mu over this denominator. So under the assumption that the magnitude of this second term, which is because S is j omega, so the magnitude of the second term is omega times C mu. So under the assumption that omega times C mu is much smaller than GM, we can approximate the short circuit current gain with this expression, which can be solved to obtain this result. So we can we already know that GM times R pi is the beta of the device, which is independent of the frequency. So it is the beta of the device in the mid-band frequency range. So we denote it by beta naught to differentiate it from this beta, which defines the current gain, short circuit current gain, as a function of frequency. So GM R pi is beta in the mid-band frequency range, which in this case is denoted by beta naught. And we realize that this expression here, it is the expression of a single time constant network. In particular, it is the expression of a low pass filter. So this is a response of a low pass filter in which the pole frequency, because there is just one pole, so this pole frequency defines the higher cutoff frequency or the higher 3 dB frequency. So the pole frequency in this case is given by 1 over R pi times C pi plus C mu. So writing this expression in terms of this pole frequency, we can rewrite the short circuit current gain in terms of the mid-band current gain and the 3 dB frequency like this. So the unity gain angular frequency is then found by putting the magnitude of this expression to 1. So remember, the unity gain frequency is defined as the frequency at which the magnitude of the short circuit current gain becomes unity. So we put the magnitude of this expression to 1, and the frequency at which this happens is called omega t or st, because I write j times omega t by st. St simply refers to the fact that this happens at the unity gain angular frequency omega t. So the magnitude of this term is beta naught divided by the magnitude of the denominator, and magnitude of the denominator is given by 1 plus omega t square over omega 3 dB square. And when we solve this equation, we get omega t in terms of beta naught and omega 3 dB like this. So since beta naught has a very large value compared to 1, beta naught square is even larger. So we can approximate beta naught square minus 1 with beta naught square, which will give us omega t as beta naught times omega 3 dB. Beta naught is GMR pi. Omega 3 dB is given by this expression. So the product is given by GM over C pi plus mu pi. So from this expression, we can find FT, which is given by beta naught times F3 dB. So if we divide this whole expression with 2 pi, so we'll get Ft as beta naught times F3 dB, which will be equal to Gm over 2 pi times C pi plus C mu. So if we look at this expression here, we can see that the unity gain frequency is given by the magnitude of the current gain in the midband times the 3 dB frequency. Now, the 3 dB frequency actually defines the bandwidth, because it is equal to the higher cutoff frequency. In this case, it defines the bandwidth of the device. Because if we look at figure 5 here, then there are no coupling capacitors. There are no coupling capacitors in this diagram. So for the BJT alone, because there are no coupling capacitors, there will be no lower cutoff frequency. In other words, the pole frequencies, all of them will be 0, and the lower cutoff frequency will be 0, which means that the bandwidth of the device is then given by the higher cutoff frequency. So F3 dB here, in this case, defines the bandwidth of the BJT, which is why FT is also called unity gain bandwidth. Furthermore, from this expression, we can see that Ft is given by the product of the current gain in the midband times the bandwidth. So unity gain frequency is also referred to as the gain bandwidth product, because it is given by the product of the bandwidth and the gain of the device in the midband. Similarly, for MOSFETs, we can use the high frequency small signal hybrid pi model, short circuit the output, and excite it with a current source IG. So in this case, following a similar analysis, we can find the short circuit output short circuit current as GM-VGS minus the current flowing through CGD in this direction from left to right. Because CGD is in parallel with CGS, because this node is essentially at ground, because the output is shorted to ground. So the voltage of this node with respect to this node is VGS. So SCGD times VGS defines the current flowing in this branch from left to right. So GM-VGS minus this current gives us the output short circuit current. VGS is given by IG times the total impedance at the gate, or in other words, the total impedance between gate and ground, which is given by the parallel combination of CGS. In fact, it is given by the parallel combination of X CGS and X CGD. So CGD is in parallel with CGS, and the net capacitance between gate and ground is CGS plus CGD. So VGS is given by IGS times 1 over S CGS plus CGD. So putting this VGS expression in here, we can solve for short circuit current gain like this. So short circuit current gain is given by GM minus SCGD divided by S times CGS plus CGD. And again, under the assumption that the magnitude, if the magnitude of this second term, which is omega times CGD, is much smaller than GM, then the short circuit current gain can be approximated by this expression, GM over SCGS plus CGD. So using this expression, we can find the unity gain angular frequency, which is the frequency at which the magnitude of the short circuit current gain becomes 1. So at that frequency, we write omega as omega t and S as st, and we solve for the magnitude of this term, which is GM over omega t times CGS plus CGD, and then omega t is really given by the ratio of GM to CGS plus CGD. Dividing this expression by 2 pi, we get the unity gain frequency in Hertz as GM over 2 pi times CGS plus CGD, where GM is actually the frequency independent transconductance of the MOSFET. That is, it is the transconductance of the MOSFET in the mid-band frequency range. A very useful tool for the analysis of amplifiers at high frequencies is provided by what is called as the Miller's theorem. And Miller's theorem is actually a method of breaking down a bridging impedance between two ports into two isolated impedances at both ports. So as shown in this diagram here, this in the circuit on the left here, this impedance V is actually the bridging impedance between port 1 and port 2. So using Miller's theorem, we can break down this bridging impedance into two separate isolated impedances, V1 and V2 at both ports. So V1 at port 1 and V2 at port 2. So in order to establish equivalence between this circuit and this circuit, because these two circuits, they have to be equivalent, we need to ensure that the current which is drawn by V1 from port 1 must equal the current which is drawn by V from port 1. Similarly, the current which is injected by V2 into port 2 must equal the current which is injected by the impedance V into port 2. So in other words, I1 must equal I and I2 must equal I. So the current I can be found from this circuit in terms of V1, V2, and Z like this. So I is actually, since I is flowing in this direction, so the voltage at this node is V1 with respect to ground is V1, voltage at this node with respect to ground is V2. So the voltage at this node with respect to this node is V1 minus V2. So I is given by V1 minus V2 over Z. And the gain in moving from port 1 to port 2 has been assumed to be K. So K is the voltage gain from port 1 to port 2. So V2 is given by K times V1. So we can replace V2 with KV1 and we'll get this expression for the current I in terms of the voltage at node 1, the bridging impedance, and the gain of the circuit. So using this expression for I, we can establish the equivalence between the two circuits by solving for Z1 and Z2 using these two constraints. So for the constraint I1 to be equal to I, we equate, so I1, which is given by V1 over, so I1 is V1 over Z1. we equate it with this expression, and a simple manipulation of this gives us V1 in terms of Z and K like this. Similarly, I2 is given by, so I2 is flowing outwards. V2 over Z2 is minus I2. So I2, because V2 over Z2 is minus I2, I2 is given by minus V2 over Z2, and this is I1. So expressing V2 in terms of V1 like this, we can solve this expression and obtain V2 in terms of Z and K like this. So Miller's theorem actually provides us with a method of decomposing this impedance between two ports into two isolated impedances, Z1 and Z2, which are given in terms of the bridging impedance and the gain of the circuit by these two expressions. So from the high frequency small signal hybrid pi model for the BJT, we note that C mu acts as a bridging capacitance between the input port made up of base and emitter terminals and the output port made up of collector and emitter terminals. Similarly, for the MOSFET, it is the capacitance CGD that acts as the bridging capacitance between the input port made up of gate and source terminals and the output port made up of drain and source terminals. So using Miller's theorem, we can decompose these bridging capacitances and break them down into two isolated capacitances at the input and output ports. So here in this circuit, I have modeled the rest of the hybrid pi model for the device by this amplifier, by this inverting amplifier having gain minus AV, and I take the bridging capacitance out. So CF is the bridging capacitance between the port 1 and port 2, and the gain in going from port 1 to port 2 is minus AV. So using Miller's theorem, I can decompose CF into C1 at port 1 and C2 at port 2. So the impedance using this formula for the impedance at node 1 and this formula for the impedance at node 2, we can find XC1 and XC2 in terms of the impedance of the feedback capacitor CF and the gain of the amplifier like this. So from this expression, we can find C1 as CF times 1 plus AV, and from this expression, we can find C2 as CF times 1 plus 1 over AV. So if AV is large, then this term is approximately 1. So C2 is approximately equal to CF. However, for large AV, C1 is a magnified version of CF. So this effect introduced by the Miller's theorem, that is by the decomposition of the feedback capacitance, this effect of increased capacitance at the input port, this is called the Miller effect. So in general, the multiplication of this bridging capacitance with the factor 1 over 1 minus K, which in turn increases the input capacitance or the capacitance at the input port by a factor of 1 plus AV. This effect is referred to as the Miller effect. So we will find Miller's theorem handy in the analysis of in the high frequency analysis of the BJT and MOSFET amplifiers. So this brings us to the end of this lecture. Thank you very much for your time, and I will see you in the next class. Take care.